Okay, this is going to be part 4, October 2024, Pearson EdXL International A-Level for Physics, Unit 5, which covers thermodynamics, gas laws, can't remember all the topics, and cosmology. No, I can't remember what's in between. Thermal physics. Anyway, this question is about astrophysics or cosmology. So it says, Sirius is the brightest star in the night sky. Canopus is the second brightest star. Show that the luminosity of Sirius is about 9.7 times 10 to the 27 watts. So that's what we've got to show mathematically. Now the equation we're going to use is this equation. It's on the list of equations. Okay, so it's luminosity is the constant times the surface area of the star multiplied by the temperature in Kelvin to the power of 4. Well, they've given us the temperature to the power of 4, and they've given us the radius. So from the radius, you can determine the area, which is the surface area of the star. Okay, so if you do that, 4 pi times the radius squared, you'll come up with an area. They haven't given it to the mark scheme, and I didn't have a calculator to put that square value in. So if you want to do it separately, you can, but you can go straight into it, and instead of putting area in this equation, don't like that, let me tidy that up. Instead of putting area in this equation, so you instead of putting area, and again, I don't know why it does that. It's when I try to do an arrow. If you put in area here, instead of putting area, you put 4 pi r squared, then you can do it in one go. So you can see I've put 4 pi r squared in here, so you can do it all in one go, which is what the examiner's done in the mark scheme. I don't go around with a calculator actually, so I assume they've done it correctly. Sometimes I check their calculations on my phone calculator, but I don't actually have a scientific calculator when I'm doing these. So you do, so you can work out the answer here, and working out the area will get you 1 mark. Okay, so if you fill in that blank there, you'll get 1 mark. And then you've got to work out the overall luminosity. Yeah, don't forget the temperature has to be the power of 4. And this is a constant. That's the value, and this is given to you in your data sheet. 5.67 times 10 to the minus 8. That gives you a luminosity to 4 or 3 significant figures of 9.685 or 9.69. Now you should really quote to 3 significant figures. Yeah? So you should really go to the bottom one, and they want you to say that to 2 significant figures, it is 9.7 times 10 to the 27 watts. So we've got our 3 marks. A teacher claims that from Earth, the Sirius appears twice as bright as Canopus, or Canopus. How do you know how to pronounce it? I've never been to these stars myself. Assess the accuracy of this claim. Well, to do that, appears, when they say appears twice as bright, they mean because of the different distance. And the appearance of brightness is called intensity. And intensity is the luminosity divided by how far away it is squared, because obviously the star's intensity of its brightness diminishes as the inverse square law. And that means it's spread over a bigger and bigger sphere, and this would be the sphere at the distance to the Earth, where d is the distance to the Earth. Okay? The distances to the Earth are given here. Yeah, the values are given. So this is the value. That's what you put in the denominator of the intensity equation. And once you do that, you can see. So you've got to do this calculation twice. You do the intensity for Sirius, which is the luminosity of Sirius, which we calculated in the first part. So the luminosity comes from there. So once you've got the luminosity and you put it into our equation, so you put this luminosity into the top of this equation. Once you do that, and you know the distance of Sirius is given to you here, it's just a matter of mathematics. As I said, this is a very, very mathematical topic, very mathematical unit. Okay, so you put the intensity 9.7 times 10 to the 27, but instead of using 9.7, let me just correct myself. We should really use the accurate value to 3 significant figures at least. So you should really use this value, not the 2 significant figures value. So that's what I did. I used 9.69 for the luminosity, and the distance was given. And when you do that, you can work out the intensity at the distance to the Earth will be 1.16 times 10 to the minus 7 watts per square meter. Okay? Now, just for comparison, the sun's intensity, which is our closest star, our sun, is about 1,300, am I remembering correct? At the equator, at the brightest time of the day. When it's overhead, 1,300 watts per square meter. So obviously a star is much, much dimmer than our sun, or appears much dimmer than our sun because of its distance. Okay? You then do, you no longer need the first part of the question. You then do the same thing. Yeah, I'm going to do this one in green. So you do it for Canopus, however you do it, however you say it. Yeah. So you do the same again, and this time that they've given you the luminosity of Canopus here. Yeah. And you put the values in. The distance is given as 2.93 times 10 to the 18. Square that distance, and you come up with a value for for Canopus of 3.82 times 10 to the minus 8. So it's less bright because the other one was 10 to the minus 7. You then divide one by the other to find the ratio, put the numbers in. To 3 significant figures, you'll get a ratio of 3.02. So based on these figures, Sirius should appear 3 times as bright, not 2 times. So the teacher wasn't 100% accurate, but who can blame the teacher? After all, they're the ones who are helping you. Okay, so that is question 15 done. Let's have a look at the mark scheme. I put the mark scheme, interspersed it with the question, my answers. So there's question 15A. You can pause the video if you want to have a look at what they're giving you marks for. And then 15B is what we just went through. So I hope that helps, having the mark scheme as well. And now we're going to go to question 16. So question 16 is an experiment. The diagram shows some equipment that could be used to calibrate a thermistor. Now, I'm not sure, but I think this might be a core practical. You need to check to be able to calibrate a thermistor. All right, so the thermistor is put in the water. I actually did this with my GCSE students the other day, and the variation made it easier than this. So we had a beaker of water. Yeah. We didn't put it on a tripod because we were not heating it. The way I did it with my students in year 10 was to put it in boiling water and let the temperature drop gradually. Yeah. So they want you to describe a method. Not that my year 10 students could do, but a student could use to obtain a calibration curve for the thermistor from 0 degrees to 100 degrees. So if it's going from 0 degrees to 100 degrees, it makes sense to use a heating method. Whereas my year 10 students, I just gave them a kettle, boiled the kettle, put them in boiling water, and then gradually added cold water to it to speed up the cooling, and got them to come up with a conclusion and see if they got a nice calibration curve, yeah? Or we didn't do a calibration, actually, we just saw if we've got a curve. Whereas in A level, they want you to calibrate the resistance against fixed points, and the two fixed points will be 0 degrees and 100 degrees. Those will be the known fixed points, and then you can use in between values to determine temperature from the resistance, okay? So I would like my students to do this in year 12, actually, before they come into year 13. Yeah, then in year 13 you can just revise it. So you should identify, it says, any extra equipment that would be needed. Well, obviously, if we're starting from 0 degrees, you would need ice. To measure the temperature, you would need a thermometer. Yeah? You would need a heat source. They haven't put a heat source. The heat source would need to heat up the water. Okay? So those are 3 things you can identify any equipment straight away. And then you need to consider the quality of your data or the accuracy. Okay? So I told my students in year 10, you've got to stir the water to make sure the temperature is even throughout the water. And you probably want to make sure you've got a lot of data points. So every 5 degrees centigrade is probably a good way of doing it. Yeah, but the mark scheme allows you to do every 10 degrees centigrade. The position of the thermometer is important. You want the position of the thermometer to be close to the thermistor. Yeah, because the temperature can vary within a beaker of water, especially if you're heating it fast. And then if that's why you should pause the heating. Wait a while before you take your readings to allow the temperature to settle and to stir it at the same time. So pause, stir, and then take readings. That will be a good way of doing it. Now, you should also make sure you read the thermometer at eye level to avoid any errors in reading. Okay, random errors. Okay, now I have copied the mark scheme. Let's have a look at the mark scheme, which may be clearer than the way I've just bullet pointed it. So let's see, where is the mark scheme? Question 16. There it is. They give you 1 for adding ice to water. Yeah. And they're saying bring temperature down to 0 degrees initially, I think. Use a thermometer. Yeah. You can use a temperature sensor instead if you want to use a data logger, for example. Measure the corresponding resistance on an ohm meter. Yes, I think they had the ohm meter in the circuit diagram. I didn't draw your attention to it. We'll have a look in a minute. State the method of heating, either a Bunsen burner or an immersion heater you could use. It says allow a water bath. Okay? And then you plot the resistance against the temperature. You plot it, obviously, because you want to calibrate it. Yeah? Resistance against temperature. And these are the 6 mark for stirring the water, placing the thermometer. These are the accuracy marks that I was saying you should try to build in whenever you're doing an experimental write-up or a method. Okay, so hope you find that useful. Let's go back and have a look at the circuit diagram. Yes, there's the ohm meter that you need to use. And you can set these on different values. So you've got to see which value your thermistor that you've got adjusts best to and gives you the range of readings that you need for the temperature variation that you're going to give it. So I hope you found that useful. So we've gone through question 15 and 16 now. I don't know how many more parts I can record, as I might need to have a break as I've been working all day. So I hope you find it useful and you appreciate the fact that I'm not actually teaching Unit 5 right now. And most of these videos I do to help me with my own job. And along the way, I upload them to YouTube, partly to help anyone else who wants to do it, partly to see how well YouTube works as a learning tool. But also, it's a way for me to keep a record of all of the past papers I've done, and they'll be there every year for students to use. And if I continue teaching for much longer, they will be a record for me to use with future classes without having to store them as PDFs or keep them on a hard drive. So I don't actually need the PDFs once I have recorded them on YouTube. So I hope you find it useful, and I hope you'll appreciate the extra hours that is put in to create these solutions for you. And the only thing I need in return is for you to like every single video you watch, share it with your friends to increase the coverage, and to subscribe, as I've said. So thanks for watching. Catch you in the next video. Bye for now.